All right, so we've just finished the second quiz, and I handed out a paper copy of the evaporation assignment. That's also posted as a PDF on MU Online, which is where you should upload the assignment. That's due a week from today. And we're going to be talking about evaporation today and Tuesday. So I think what we're going to discuss today in class may help you to get started on these book problems. And then on part 2 on the assignment, some of it is just looking up data online. And so you don't need any specialized knowledge to do that, to download the data and start to organize some of the numbers. Some of the calculations you may not be able to do until Tuesday, but you can definitely get started on that assignment. So we're talking about evaporation today, and we're going to begin by looking at a couple of videos just to whet our appetites for the subject. Nice, right? Hopefully the lecture doesn't evaporate your interest. All right. All right, so we literally watched a puddle dry in class today, right? It's like paint drying, but without the color. All right, so time lapse here. Why is the water evaporating? Why doesn't it stay water? Like, why is the water going away? Is it because the temperature in this location is above 100 degrees Celsius? Because that's the temperature that water boils, right? So, and like maybe this is Arizona or something, but it doesn't get 100 degrees Celsius in Arizona. Even someplace like Dubai where it's piping hot, it only occasionally, very occasionally gets up to 50 Celsius. So we're only halfway to boiling there. So if water boils at 100, why is it that it's going from a liquid phase to a vapor phase? Nobody's jumping out of their seats to answer this mystery. Maybe the next video will tell us. YouTube has the answer to all things. Here's the Leidenfrost effect. It's sizzling water. Okay, those, oh, I wanted to make it full screen. I'm not sure why it isn't. All right, so in this video, there are droplets of water on a pan that's so hot that actually it's evaporating on the underside of it, and so the water droplets are moving around because it's kind of like when you play air hockey. You know, there's a cushion of air underneath the little plastic puck. So here, there's a cushion not of air, it's water vapor underneath it. So this is evaporating so quickly. The previous video we watched was a time-lapse video. The evaporation was occurring very slowly. And this one, the evaporation going from a liquid phase to a vapor phase is going very quick. So what's the difference between slow evaporation and fast evaporation?
More energy.
Yeah, there's more energy here. This frying pan, you can't see it, but we presume that there's a gas flame under there. Yeah. So this is a really hot frying pan. And in the previous example, that concrete wasn't 400, 500 degrees like this frying pan is, and so that's why it evaporated more slowly. Can you believe 12,000 people have watched a video? How come my videos only get a couple hundred views and this gets 12,000? All right. Here's evaporation in Canada. I guess maybe the past 2 videos are evaporation in the United States, so maybe Canadian evaporation is like more polite or has an interesting accent. Let's see. I'm really sorry if I get it wrong. Not amazing, but all right. So in Canada, the water does evaporate differently, actually, because here in the United States, if I had a hot, boiling kettle of water and I tossed it out at you, it would scald you. It wouldn't evaporate in the air before it hit you. It would scald you, and I'd be in real trouble if I did that. So in Canada, though, Who can explain this behavior that we just saw? What's going on there? First of all, what's all this white stuff on the ground? Because I think that gives us a clue. Snow. Yeah, it's really cold temperatures. You can do that in West Virginia, and actually I have. There were a couple of days, I think 3 years ago, where the temperatures were below 10 degrees Fahrenheit overnight. And I remember that very clearly because I was waking up every hour on the hour to throw more logs in my wood-burning stove just to keep the house above freezing. It was really cold. But in the morning, we did this because I'd seen this video before. Now, 10 million views, yeah, that deserves it. But negative 30 degrees Celsius in Yellowknife, NWT, Northwest Territories, I think. Anyways, it's really cold there. And so it's not just the temperature of the water, but it's also the gradient between the liquid and the air. You know, like the driving force, the difference in temperature between the liquid phase and the vapor phase. And we'll get into that when we look at some numerical models we have for predicting the rate of evaporation. They take into account air temperature and water temperature. All right, now just one more evaporation-related video, and I think I showed you something similar to this in fluid mechanics. So again, this process of going from a liquid phase to a vapor phase. And we can see there's actually some condensation on the rim of the glass as the water molecules that were previously a liquid, they vaporize, and then the ones that are near the edge recondense on the outside of the cup. And so in this case, it wasn't the heat of the liquid that's forcing it into the vapor phase, but rather it's the lack of a vapor pressure above the liquid that normally is keeping it in check. And so what it does is it needs less energy to escape from the liquid phase when the air pressure is lower. So there's a latent heat of vaporization. It's a physical constant for water, we'll look at in just a minute, that's a function of the temperature. But you need less heat inside of the liquid it evaporates more quickly when the surrounding air pressure is lower, I guess is what we could say. And if you keep this going long enough, it'll actually turn to ice because all of the heat that's in the water will be used up evaporating the water.
I can open that up.
I don't think she takes it all the way to ice. All right. It's always nice to watch videos. All right. So on the Earth's surface, what drives evaporation normally isn't strange pumps, and it isn't tea kettles, but rather it's just the energy from the sun. And so where we need to start a discussion of evaporation is by looking at solar radiation and understanding a little bit about the sun's energy that it comes to the Earth, and then a fraction of that energy is reflected back into space. And your textbook has this figure, which is kind of interesting. It shows the difference in the wavelength of energy that's coming into Earth, which is relatively low wavelengths in the ultraviolet and visible range, and then what's reflected off of the Earth's surface back into space is infrared energy at a longer wavelength. And this figure up above is showing different gases and the spectrum of light that they absorb. And so part of the reason why we're able to have incoming solar radiation is that there's a relatively low absorptivity in the wavelength of visible light. Ozone absorbs a little bit of that energy, but for the most part it passes through the atmosphere. There is a lot lower wavelength ultraviolet light and infrared that is filtered by the atmosphere, but there's this band of very low absorptivity that allows the incoming visible radiation to come into the Earth's atmosphere. So if you think about, let's normalize the solar constant. On average, if we were to have 1 square meter of solar panels in space pointed directly at the sun, at the Earth's atmosphere, the closer you get, the greater the intensity is. But where the Earth is located, the Earth's orbit around the sun, if we had 1 meter pointed straight at the sun, and if it was 100% efficient at converting radiation, the solar radiation into electricity, we could get 1367 watts per square meter. That's the solar constant. So let's just say on a percentage basis that that's 100% of the energy that's coming in from space. Well, a lot of that gets reflected. Some of it is reflected in the upper atmosphere, some of it is reflected by clouds, some is reflected by the Earth's surface without being absorbed and then re-emitted. So this figure on the right is talking about the energy that's emitted back into the atmosphere. And the difference between this reflection by surface and that which is emitted is that the heat that's absorbed by the surface is returning as long-wave radiation rather than reflection, which remains as short-wave radiation at the lower wavelengths in the ultraviolet and the visible spectrum. And so there's energy balance here. If we add it up, if we add everything up, we've got 100 units coming in and 100 units going out. Whether it's going out by reflection or going out by long-wave radiation, there isn't a constant accumulation of heat, not at least on the relatively short term. I mean, there's global warming, which is increasing the amount of energy that is trapped in the atmosphere, but we're talking, a couple degrees Celsius over decades, whereas this is a balance on more of a short-term basis. Here again is just another figure taken from the text that contrasts the different wavelength of the incoming radiation and the outgoing radiation. And part of the calculations that we do look at the intensity of the sunshine and the temperature of water, and it's trying to predict how quickly water is going to evaporate on the basis of how much incoming solar radiation is available. And so in cloudy areas, there's going to be obviously less evaporation. The water is evaporating more slowly than in areas where the intense sunshine is driving this process a lot more quickly. So the northern latitudes have less solar radiation, partly because the sun's rays are coming in this direction, and then you can see that those rays are projected, since the Earth's surface is spherical, it's projected over a larger land area than, say, at the equator, where you have this incoming incident area being projected over a surface area that's approximately the same size. I think this figure does a really nice job of kind of illustrating why the radiation in the northern latitudes is not quite as high. But of course, the Earth tilts during the seasons. Right now, we're at the point where the Earth is about straight up and down. We're getting close to the equinox. That's tomorrow, actually. It's a day that tomorrow we'll have 12 hours of sunlight and 12 hours of darkness. In fact, that's what this figure shows. It shows that on the 22nd of September, we have the autumnal equinox. And at the North Pole, the equator, and the South Pole, everywhere has 12 hours of darkness and 12 hours of daylight. The vernal equinox in the spring is the same situation, but in between those two periods, the Earth is tilting during what we have as our summer in the northern hemisphere, is where more of the top of the globe is tilted towards the sun, and that's why it feels like summer to us, is that we have more solar radiation being absorbed by the northern latitudes. And then during our winter, we have shorter days because, as you can see, this figure makes it pretty clear that the distance in the northern latitudes, it's going to be exposed to sun. If you were to trace that length, it's going to be lower than the length that's going to be in darkness during our wintertime months. I think I've told you I went to Iceland a couple of times, and I was there not quite during the summer solstice. I was there a couple of weeks after the summer solstice, like June 30th I was there. And at night, I mean, it's not all the way north, and so they don't have continual daylight. The sun does set, but it only goes down below the horizon not very far, so that, you know, in the morning, even before the sun comes up here in West Virginia, you can still kind of see your way around in the 30 or so minutes before sunrise. The same is true in Iceland, although it's not technically daylight because the sun does dip below the horizon. It's still, you can see. It's just dim rather than dark. Okay. Humidity is part of what we're going to have to think about when we talk about evaporation, because there's two ways to approach evaporation modeling, and one is looking at the amount of energy that's available to drive that vaporization, and then another view of how quickly water is going to evaporate looks at how far away you are, how far the air is from being fully saturated with moisture. And so you can probably guess that if we had a pan of water and we took it to the Gobi Desert, which is very, very dry, then at the same temperature and the same solar radiation, that pan of water is going to evaporate more quickly in a dry environment than it would in a humid environment. You know, if you have 90% humidity on some tropical island, even if it's at the same latitude with the same temperature and the same solar radiation, it's not going to evaporate as quickly because the driving force is partly about the energy available for volatilization, but it's also the distance between how humid the air is and how humid it can be at full saturation. So water vapor can exist as a gas even when the temperature is below 100 degrees Celsius, because some of the kinetic energy of molecules is above the kinetic energy needed for volatilization. And let's just say we have a scale and it's 100 degrees Celsius is where water will begin to boil. But if we have some water, like a pan of water that's at 80 degrees Celsius, that's the temperature of the water, the amount of kinetic energy in that water varies, and there are going to be some molecules that have relatively less kinetic energy, although on average the sample has a temperature of 80 degrees Celsius. That doesn't mean that every molecule that is in that system has the same amount of kinetic energy, because there may be a series of collisions where a couple of molecules bump into each other, and then the resulting collision goes into another molecule that already had high energy, and so some of them are bouncing around pretty quickly and they have high enough kinetic energy to escape as a gas. And in fluid mechanics we talked about the idea that when you have a liquid, the atmosphere is pushing down with some vapor pressure trying to resist, pushing down with an atmospheric pressure trying to resist the evaporation of the water. And we measure the tendency of a liquid to go into a gas, P sub V, the vapor pressure. And we talked about how when the temperature increases, the vapor pressure gets higher and higher until once we have the vapor pressure equal to the atmospheric pressure, there's a steady boil, or a really vigorous escape from the liquid phase to the gas phase. But even before the vapor pressure exceeds the atmospheric pressure, there are going to be a fraction of the molecules with enough energy to escape. A distribution of kinetic energies. So it's the heat and energy from the sun that keeps water vapor as a gas. And there's a constant exchange between the water in the atmosphere and the water in the liquid at the Earth's surface, the lakes, rivers. The water molecules are always cycling between the two as there's precipitation and then evaporation again. So if we zoom in on a liquid surface and we think about the liquid itself is where the water molecules are tightly packed together and bound through attractive forces, but some of the molecules escape and overcome the vapor pressure that's holding them in the liquid phase. The amount of gas above the liquid layer, we measure that as the atmospheric pressure. And the quantity of water molecules, how much water is above in the gas, is the relative humidity. And what causes the liquid to vaporize is energy. Now, on an average across the entire Earth's surface, the rate of liquid evaporation is 3 millimeters per day. And the evaporation is much lower at the poles than it is at the equator because there's less energy there. And there are places where there's essentially no evaporation, like in deserts, where there isn't any liquid at the surface and the top layer of soil is fully dried out from the heat of the sun. So this temporal average can give you maybe the wrong idea. There are places where the evaporation is probably triple or maybe even 4 times this high, and other places where the evaporation is 0. A physical property of water, the latent heat of vaporization, tells us how much heat is required in order to take a kilogram of water and turn it from the liquid phase into the vapor phase. And so this is in terms of joules, and as it's written here, the temperature needs to be in degrees Celsius. There is a point of confusion sometimes. This same latent heat of vaporization is sometimes listed in kilojoules per kilogram, but here this is 2.51 times 10 to the 6th joules per kilogram. Here's a picture that I took while I was driving a couple of years ago. Not the safest thing. It's along Route 2, and this is the Ohio River. And this isn't the first time I'd seen this. I've seen this on a lot of occasions where there's like a thin cloud that's just hanging over the river. Has anybody else seen this before, where it's a clear blue sky, but there's like a cloud that's staying over the river? So based on what we've talked about so far, how could you explain something like that? What causes clouds? Okay. Evaporating water, lifting. All right, so this picture was taken in the, I think in the early fall. The trees are still green. So the air was cool, but water cools more slowly than air does. In other words, in the mornings these days, we're getting temperatures in the upper 50s or so. The river is still warmer than that. And so the air that's touching the river is warmer than that. And so if you have a section, some mass that's warm and everything surrounding it is cool, then the air is going to rise above the warm thing. That's the idea behind convection. And so I think what we're seeing is the effect of convection, where the moist air that's warm above the river is rising relative to the cool air surrounding it. And then as it rises, it's cooling, and that's where this condensation is forming, the cloud. And so it doesn't necessarily rain, because as it evaporates and rises, it's just diffusing into the drier, cooler air that surrounds it. But I still think it's a pretty cool phenomenon, so that's why I risked life and limb to take this picture through my dirty windshield. Here's a similar figure to one that we already looked at, just looking at the distribution for the incoming solar radiation and how some of it is reflected as short wave, some of it is absorbed, and then re-emitted as long wave evaporation. And you don't necessarily need to memorize the relative fraction of energy that's lost to each one of these processes, but it does help to explain the varying rate of evaporation in different places that have maybe more cloud cover is going to mean lower evaporation because you have less energy to drive evaporation, or places that have relatively low humidity will have faster evaporation. And I've already addressed the fact that if we didn't have the incoming radiation and the outgoing both equal to 100%, then that would mean that there's a net accumulation of heat in the Earth's atmosphere and that the Earth would be getting rapidly warmer. All right, so for modeling this, I'm going to start by telling you about the energy balance method. And the energy balance method answers the question, how much energy is there to satisfy the latent heat of vaporization? Now that's that constant that says how many joules of heat is required per kilogram of water going from liquid to gas. This model is predicting how much energy is being delivered to the Earth's surface. And just to begin thinking about it, let's say that we have a control volume, and inside of the control volume is some water. And we're going to keep track of the movement of things through the control surfaces that surround the control volume. This may remind you of the Reynolds transport theorem that we took a look at in fluid mechanics, where we said that we're going to keep track of the accumulation of something inside of the CV, which is control volume. And so this is a storage term. And then we're going to have a transport term where we look at the movement of mass through control surfaces. That's what CS stands for. And so the control surface that we're most interested in here, if we assume that this pan is impenetrable, there isn't movement of water down into like the Earth's surface, we're mainly going to be interested in looking at the movement of water above the liquid surface. Now here E stands for evaporation, and it, you can see, is negative dH dt. So we're saying the height of water inside of the control volume is getting lower and lower over time, and so E is a rate. It's the rate that the water is evaporating, and assuming the pan is impenetrable, there's just a net decrease of water in the storage of the liquid phase. So we're so far just confining ourselves to what's happening to the water during evaporation. The water level is going lower, and there's some change in volume over time. If we multiply that volume by density, that's what's accounting for the change in mass over time inside the volume. So m dot is a mass flow rate, and the negative sign is just suggesting that the amount of mass inside of this control volume is decreasing over time. So if we rearranged that, what we could come up with as a conclusion is that there's some pan area, the surface area that the water is evaporating over, and if you multiply the area and the evaporation rate by the density of water, then that is the rate that the mass of water is vaporizing. So it's going to directly go, even though liquid molecules take up more space once they evaporate, the mass is conserved. So the rate of water decreasing in the control volume is going to be the same as in the gas phase we have vapor flowing out. So here the vapor flow rate that they're saying m dot v is the same as the liquid phase, the rate of evaporation in the liquid phase. So here's that vapor phase mass balance. It's saying we can have the humidity of the air, the specific humidity, the mass of water relative to the mass of air. So the density of air multiplied by the specific humidity is going to be the amount of water that's in the air. multiplied by the changing volume, we're going to say that there's no movement of, there's no accumulation of water vapor in the control volume in steady conditions. And so there's just transport out. And the rate of evaporation, is going to be how quickly the water is moving through the surface. That top area is the area that we would use as our top control surface. And V here is the velocity that the air is moving out, in contrast to the V with the cross through it, which is meaning volume in the previous steps. So V times A is a volumetric flow rate. Then we have the density of the air multiplied by the specific humidity. So the rate of evaporation out. So keeping all those concepts in mind, we also have to think about how much heat is available in the energy balance method. Now, again, we've got the latent heat of vaporization, and the amount of heat that's available is going to be the radiation that comes in, R sub n, the net radiation flux, minus the heat that is going to the air by the water, and the ground heat flux. And so the radiation that comes in is going to be driving evaporation, but then it's also going to go other places. The radiation that's coming in from the sun, some of it's going to cause the water to vaporize, but then some of it is also going to go to heat up the air, and some of it's going to heat up the ground. So we have to subtract out the amount of radiation that is going other places before we start satisfying how much heat is used to vaporize the water. Now, this net radiation flux is less than the radiation that's coming in to the Earth's atmosphere, because we have reflection and emission. So this is showing that your R sub I would be the sun's radiation that made it through the upper atmosphere, and it's getting close to the surface. So there can be reflection off the surface of the water, and then there's also emission of radiation from the water, just because the long wave radiation that's at a different wavelength, but it's still energy that's being lost by the water. And so the water can't evaporate using this energy, because this energy is being reflected back out into space. So dH dt is the rate of heat that's going into some mass of water. And we said it was heat that was driving evaporation, and so the rate of heat that's coming into the water is going to be the net radiation minus those other factors. And what we can do is, assuming that we're not losing any heat to the air by the water, and we're not losing any heat to the ground by the water, then that is a pretty big assumption, but it's true for out in the open water. If you've got water just in contact with other water and not immediately adjacent to land, then we can finally say that it's the amount of energy that's available for evaporation is that net radiation divided by the latent heat of vaporization and the density of water. All right, so just to kind of demonstrate how all the pieces fit together, we're going to look at this energy method for predicting the rate of evaporation in a lagoon, where we have the incident radiation being measured as 978 watts per square meter. And you'll remember that that's lower than the radiation out in space, which was closer to like 1,400 watts per square meter. So we've got nearly 1,000 watts per square meter at noon on February 12th. We've got a water temperature measurement, which we can use to calculate the latent heat of vaporization. We've got the air temperature measurement, which we're going to be needing later on when we do the same example according to a different method. The relative humidity is given. Again, you don't use the relative humidity yet in this energy method, but we will use it for a different method along with the wind speed. But let's just use this energy approach to estimate what the evaporation rate is going to be in millimeters per day. Now, a word about the units here. This evaporation rate, you're going to get in meters per second. The units that come out of that, E sub r, the evaporation rate, is meters per second. And so you need to convert it from meters to millimeters and then from seconds to day to get the rate in the units that are needed in this problem. So the first thing to do is just calculate the latent heat of vaporization for the water temperature that's given of 20 to 26 degrees Celsius. And then look at the radiation constants. Now, we can estimate how much radiation is being emitted by the temperature of the water, this R sub E. The reason why the water temperature is given is even if you don't have like a sensor that's directly measuring how much long-wave radiation is coming out from the water, you can estimate the amount of long-wave radiation emitted by water using the temperature of the water and then the Stefan-Boltzmann constant, and a constant called the radiation emissivity of water. So R sub E you're going to be estimating based on the water temperature. All right. So I'm going to pause the recording, give you some time to start plugging numbers into there, and see if you can calculate E sub r in terms of millimeters per day. So here in the solution, what I started with was just sort of putting all the constants that we know out there, and then start by calculating the radiation emitted by the water, because this is all about this energy balance method is trying to find out how much energy can drive vaporization. And the energy that is going out into space through long-wave radiation isn't going to be contributing to the rate of evaporation. So this is saying of the incoming solar radiation, we have to subtract out the radiation that's then being emitted, because the difference is going to be driving evaporation, but not all of the incoming radiation is driving evaporation. So this long-wave radiation emitted 451.8 watts per square meter based on the empirical estimate here. It's using the Stefan-Boltzmann constant. And so then the would pan. Oh, it shows what I know. Okay, so the net radiation available to drive evaporation here then will be 183.9 watts per square meter, because we have the incoming 978. Some of that's going to be reflected. So 1 minus 0.35 is saying 35% of it is being reflected, so 65% is not reflected. 65% of this 978 is absorbed, and then we have to subtract out the emission through long wave, and that only leaves us a measly 183.9 watts per square meter to drive the vaporization. So then the latent heat of vaporization is saying, based on the temperature of the water, it's going to take us 2,439,380 joules per kilogram. And then here in the margins, I make the note that the units are equal to watt-seconds per kilogram, just because if we want to look at how the units cancel out later. Any questions so far? Now, this density of water is based on the temperature of water being at 23 Celsius. Or was it 26 is the water? Yeah, okay, 26 Celsius. All right. Sorry that I've got some corrections in here, but it's sloppier than even usual. The E sub r is estimating the rate of evaporation just based on the amount of the energy availability. And so we're saying if it takes this much energy per kilogram to evaporate water, and this is the density of water, we want to think about in a volumetric basis how quickly the water is evaporating. So that's why we're taking this physical property of water, which is energy per kilogram, and multiplying it by the density. And then this radiation term up here, you'll notice it's per area. So it's watts per square meter. So the units actually do work out here that we have meters per second, the rate that the water is going to be evaporating on a meters per meter basis, a square meter per square meter, because we've taken into account the radiation intensity and the density of water. So in the end, it should be 6.54 millimeters per day. All right. Any questions so far? It's called the energy method. So when we get together on Tuesday, we're going to use a method that's called the aerodynamic method, which is looking at the same problem from a different direction. It's saying, well, this is how much energy is available, but we also have to account for what's the capacity of the air to absorb this moisture, because there is a limit to how much moisture the air can accept. When the relative humidity is 100%, then it doesn't matter how much energy there is. It's just for every molecule that comes into the air, one has to go out of the air back into a liquid if you had 100% relative humidity. So the aerodynamic method considers transport. And so it considers the movement of air across the surface and the relative humidity of it. And then finally, there's a combined method that averages a weighted average of the energy method and the aerodynamic method. And so it's saying in the combined method that both of these factors sort of contribute to the overall change in energy, both the energy availability and the rate of transport away from the liquid surface. All right, but that's all for today. Just a reminder that this homework assignment I've given you is due a week from today, and you could start to familiarize yourself with these problems, but you'll have everything you need after our lecture on Tuesday.